My YouTube math channel. So in my previous video, I talked about the antiderivatives, that they are the reverse of a derivative. It's the reverse process of a derivative, and we were able to see a pattern, and we were finally able to kind of informally write or kind of deduce the power rule for antiderivatives. Guys, in this video, I want to actually put it in a formal notation, and I also want to introduce the notation for antiderivatives. Like we have a notation for the derivatives. Usually we use the primes, y prime or fx prime, or we use dy over dx depending on what we are differentiating with respect to. Similarly, we have a notation for the integrals. Guys, keep in mind a very simple idea for integration or integrals or antiderivatives is that it is basically the sum of the areas under a curve. Okay, so when you think about the sum, you have like an S or a sigma notation. So this notation right here is kind of motivated by the sum. So you can think of this as a sum or a sigma notation kind of extended. So that is this notation which for integrals, and then it is always like with respect to something. So in this case, f of x, this is the function that we're trying to find the integral of. And in this case, since the function is in terms of x, so we are integrating also with respect to x. So if function is in terms of y, then it would be with respect to y. And it, again, there's so many things that can happen here. But to begin with, guys, most of the times you will have to integrate or find the antiderivatives with respect to x. And then, guys, the idea of these two, you can think of these two as like, since we're talking about thinking about the area, so area is like length times width. So you can think of one of these as the length and the other one as the width. So it's basically extension of the idea of sum of the areas under a curve. And this is how we formally write it. This is called the integral of this function f of x with respect to x. Okay, so guys, from the previous video, we already kind of know what the power rule for integrals is. So let us formally write it up. So the integral of x to the power n, so now we can introduce the notation because we just introduced the idea of this notation. It's with respect to dx here because the function is x here. And guys, that equals to, this is something we kind of deduced from my previous video where we looked at a pattern and we were able to figure out that the integral of the x to the power n, or the power rule, which is also called as the power rule for integrals. So we had a power rule for derivatives, now we have a power rule for integrals as well. So it's going to be x to the power, and we figured out, looking at the pattern, that you have to add 1 to the exponent, and we divide by the same thing, n plus 1. And guys, there's one more thing that we have to use here, which we didn't really talk about in my previous video, which is called the constant of integration. So whenever we are evaluating indefinite integrals, we are always going to have a constant of integration. It could be any positive or negative number. When we actually go into the definite integrals, then actually we'll be able to figure out what that actual constant of integration, the value of that constant of integration is. So guys, here I want to kind of, again, informally with an example, I'm going to illustrate what is this constant, where does this constant c come from. And I mean, I know from my experiences when I teach this course, my students are always looking at this constant, they're wondering where does this come from, and I want to make sure that they know where this constant kind of comes from. Okay, so guys, I'm just going to look at an example and let us see and try to understand this this idea of why there's a constant here. So let us think about a function. So let us think about a function, and before I give you the function, let us say we know the derivative of the function. So let's say the derivative of the function is and I'm just creating and coming up with an example, 4x cubed. So guys, if the derivative is 4x cubed, then what is the function whose derivative is 4x cubed? So it's not too difficult. I chose an easier one. So obviously the function is going to be x to the 4 because the derivative will be using the power rule 4x to the power 4 minus 1, which is 4x cubed, right? So that's pretty simple. Now guys, look here carefully. Now if I change this function, I'm going to change this function. I'm going to play around with this function. So if I change it to x to the 4 plus 2, then guys, what would be the derivative? Well, the derivative of x to the 4 is still 4x cubes. And then derivative of the constant, we know the derivative of a constant is 0. So there's nothing more with it, right? So here, let us also remind ourselves, I think we need more room here. So what I'm going to do is I'm going to get rid of this, and then we are going to put it back here somewhere if we have space. Otherwise, we already know it. Guys, if this is true, now we understand the whole idea of antiderivatives. then can we simply say that the antiderivative of 4x cubed with respect to dx, we know why we have to use the dx, it's in terms of x, so we got to do it with respect to x. So can we say that this equals to x4? This is, I'm just using the basic definition for an antiderivative or an integral. It is the reciprocal of a derivative. If the derivative of this is this, then the antiderivative of this better be that. Okay, and we can easily verify that now using the power rule. We have the power rule. Okay, guys, similarly, let us see here. If I take the antiderivative of this, and now I will have to base it based on this function, because this is the derivative of this function. So I'm going to use this function when I write the antiderivative for this. So antiderivative for 4x cubed should be this function right here, which is x to the power 4 plus 2. Right? Let us write few more examples. So let us say if I change this to x to the 4 minus 352. I'm just coming up with these some numbers. Guys, what is the derivative of this function? The derivative of this function would still be 4x cubed. And when I take the derivative of that constant, whether it be minus or plus, it's not going to matter. It's still going to be 0. So what does that mean? That means the integral of 4x cubed from this example right here, this number 3 here, is x to the power 4 minus 352. So we are getting somewhere here. So guys, let us say I use this, I have a function x to the power 4 plus any constant, and that constant could be a positive number or a negative number. Then what would be the derivative of that function? Still 4x cubed, right? Still 4x cubed. Constant, the derivative of a constant is 0. So what can I deduce in terms of the antiderivative or the integral? It is going to be still x to the power 4 plus a constant. So every time, we can see that every time we keep adding or subtracting numbers, like we can think of this as adding a constant, the antiderivative is going to be like there's going to be that constant right there, because we have to think in terms of, we have to think like the reverse. If I take the derivative of this, I still get this back even from here and here and here. So that adding that constant actually does not really change anything, right? So that is like one of the ways to kind of see where that constant c comes from. So guys, please like look at this carefully and see like the pattern here, that constant does not really matter when you think in terms of the derivatives, and you know antiderivatives are just the reverse of that. So that is where that constant comes into play. Okay, so let us actually write the formal definition for the power rule here. Again, I'm going to get rid of some of these things right here. So I think we can get rid of this, and I want to write it back here. So guys, this here we have the power rule, which is integral of x to the n dx equals to, and we know it's x to the power n plus 1 over n plus 1, and then there's a plus c. And now from this example or this exercise, we kind of know that this c is not going to change anything, so we can keep on writing the c. And it is very important for us to keep on writing a c till we go to definite integrals and where we actually evaluate or find out the exact value for c. Guys, there's one last thing that you have to be careful with while you are using the power rule, which is the fact that the n cannot be equal to -1, and that's not too difficult to see, because look at the denominator here. If n is -1, then -1 plus 1 becomes 0. Then we get into all this trouble of dividing by 0. We cannot divide by 0. So that's why we cannot use this power rule when n is -1. When n is -1, then we have a different formula for the integral of those types. So we are going to write those in my next video and few others. Finally, there's guys so many different formulas. You have to get a formula sheet, or you have to use a textbook as a reference when you are solving examples. So this is the power rule for integrals, and then we're going to write some other rules in my next, and we're going to probably write this one as well and some other rules, and then we might also see like how we derive some of those rules, and then finally we're going to use these rules to solve examples. Okay, guys, this is just the beginning of this section. There's so many different types, and there's so many different examples. There's a huge variety of examples for integration, and we are going to like look at them, and we're going to try to do as many types as we can. Okay, so guys, try to understand the basics of antiderivatives. I would highly encourage you guys to actually read through this these sections in your textbooks which talk about or introduce this whole idea of antiderivatives, and then from there we will like use the formulas and start working on the examples. But get those basics right before we start actually doing the exercises and examples, guys. While we start doing the examples, probably we may not